Hi guys, welcome to our AP Review Day 7 practice session where we are going to be working with 4 different FRQs that all involve using a table of values where we have to be able to read them and apply them and use them to determine different things. And so in this video, I'm just going to walk you through the first one, 2004, Form B number 3, and then have you practice the remaining 3. So let's get to it. So first thing when we're reading or doing an FRQ is we want to make sure we kind of process all of the given information up front. So a couple different things. We are told that this plane is flying in a straight line with positive velocity. That word positive will come in handy later. It gives us the units here, miles per minute. So these are all miles per minute values, and then these are all minutes. It tells us V is differentiable. That's helpful too because that implies it's continuous as well. And then it tells us that this table here is giving us selected values. So these aren't the only values of velocity. These are just selected values at 5-minute increments over the interval from 0 to 40. Okay, so then in part A, the first thing it asks us to do is find a midpoint Riemann sum with 4 subintervals of equal length to evaluate this integral from 0 to 40 of v of t, that's this function here, dt. So a Riemann sum is a rectangular sum where we are finding different base times heights and adding them up. And in this case, we're finding 4 rectangles, base times height, base times height, base times height, base times height 4 times and adding it up. So the subintervals need to leave a midpoint. So it wants us to break 0 to 40 into 4 subintervals. So those will each have a base of 10. So this would be interval number 1. This would be interval number 2, number 3, and number 4. And you can see that in each interval, there's 3 points, a left endpoint, a midpoint, and a right endpoint. So it's these midpoint values that we are going to use to determine the height of each rectangle. So remember the base of each rectangle is always the change in x, or in this case, the change in time. Okay, delta t is our base, so that's a base of 10 for each of these rectangles. And then the height is always based off of the y value, the distance from the x-axis to the curve. So that's what we need, but we have all these different y values for each interval, so when it says using a midpoint sum, they're helping us decide, okay, you need to use the y value that's assigned to the midpoint of the x subinterval. So these are the heights I'm going to use, 9.27, 2.4, and 4.3. Let me do my work down here for part A. So for my Riemann sum that I'm using to approximate this integral, which is the area under the velocity function from 0 to 40, I'm going to use a base of 10 for all of my subintervals. So I'm just going to write the 10 ones and then add up my 4 heights, 9.27, 2.4, and 4.3. So adding up those numbers, I get 22.9. And then when I multiply that to get to 10, I get 229. So side note, even though it wasn't asked in the question, I just want to point out that this would be in units of miles because it's the antiderivative or area under velocity, which is in miles per minute. So we're kind of going backward to the antiderivative, which would just be change in position, which is in miles. And actually that's the second part of this question is asking us, oh, it does tell us right here, using correct units, so that would be the correct units, miles, explain the meaning of this integral. So typically the integral of velocity is defined to be displacement or change in position. And the integral of the absolute value of velocity is described as the total distance traveled. But earlier in the problem, we noticed it told us that the velocity values are positive. And so that tells me that this integral is equal to what it would have been if I took the absolute value of velocity because the velocity values are already always positive. So these two integrals are equal, which tells me that this integral is actually referring to the total distance the plane traveled. It's traveled in miles. So this means the plane traveled 229 miles in the first 40 minutes. So it's the total distance traveled in miles during the first 40 minutes of flight. So moving to part B, where we are being asked to determine the smallest number of instances at which the acceleration of the plane could equal 0. So we have to know a couple things. The first thing we have to understand is that acceleration is equal to the derivative of velocity. Okay, so we are not going to be looking at when these values of velocity equal 0, but rather when their change in velocity over change in time, which is acceleration, is equal to 0. So that's thing one. Thing two is we have to understand we're going to have to justify our answer. So notice it's not saying when, asking for when acceleration is 0. It's just saying how many times could it be 0. So this is asking us to basically prove the existence of a particular derivative value, which is ringing to me that it's going to require MVT. So we use MVT, mean value theorem, whenever we're trying to prove the existence of a particular derivative value. And in this case, we're trying to show that the derivative of velocity, i.e. acceleration, is equal to 0 at some point. Okay? So the thing about mean value theorem is, the main statement of it says this: as long as your function f, or in this case v, is continuous and differentiable on a particular interval, then its derivative at some point on that interval will equal the average rate of change, which is determined by this difference quotient right here. So in this particular problem, what we want to do is see if there's ever a point when that average rate of change of velocity is equal to 0. So we come up to our table and start looking at my different changes in velocity, and something that I notice is that the velocity goes from 7 at time 0 back to 7 at time 15. So if I were to do velocity at 15 minus velocity at 0 divided by 15 minus 0, it would be 7 minus 7 over 15, which is 0. So there's at least one instance where the average velocity is 0. And then you might be noticing another one now that we kind of see what we're looking for. I noticed that there is another interval. So we're looking for intervals, right? Places that where the change in velocity over the change in time would be 0. So the other one is from 25 to 30. So velocity at 30 minus velocity at 25. Again, we would have 2.4 minus 2.4 over 30 minus 25 is 0. And that would be a second instance where the average, not average velocity, average acceleration, the average change in velocity over change in time is 0. So these are two places where the average acceleration of this plane is 0. So the answer to this question is 2. That's the smallest number of instances, but now we have to justify it. So here's how we're going to do that. So earlier in the problem, it told us v is differentiable on this interval 0 to 40, and the fact that it's differentiable implies it's continuous. So we're going to say this. Well, we will say, since velocity is differentiable and continuous on the interval 0 to 40, then there are at least 2 instances when v prime t would be 0, given that v of 15 minus v of 0 all over 15 minus 0 is 0, and v of 30 minus v of 25 all over 30 minus 25 is equal to 0. So we could show that there's 2 places where the average derivative, the average rate of change, is 0. Therefore, the instantaneous derivative must be 0 at least 2 places. And this is by the mean value theorem. So we want to make sure we reference the name of that theorem in order to get the point for justification. But when we reference the theorem, we also have to reference the conditions. Velocity is differentiable and continuous on the interval. And we want to show there are at least 2 instances. Oh, I should give the time intervals. So let me list those. There are 2 instances when the derivative of velocity is 0, given that these are the average rate of changes that are equal to 0. We could say these instances occur on the intervals 0 to 15 and 25 to 30. So basically what we were looking for was where change in y would be 0, right? And there were 2 times, here and here. But to prove it, to justify it, we have to be a little bit more formal. We want to reference the name of the theorem. We want to state the interval that the function's differentiable continuous on. We need to show these 2 difference quotients. And we should probably restate those intervals to be, again, more specific at the end. So these are the 2 intervals where the 2 instances are that we know of where acceleration must be 0. So moving on to part C, this function or this question is giving us a new model. So it gives us another function f of t to model the velocity of the plane on the same time interval, 0 to 40. And it wants us to find the acceleration of that plane at a given time. So this question is really more testing, again, to see if we understand that acceleration is equal to the derivative of velocity. I'm calling it f prime here since that's the name they gave it here. But that's really what they want to know or want to see if you know. And so basically all we need to do for this is just find the derivative of this function and then evaluate it at 23. Let me get rid of some of my scratch work here so I can have some room to do this one. Okay, so basically what we need to find is f prime of 23, derivative of this velocity function evaluated at 23. So to do this, I'm actually going to use the n-derive feature on my calculator, which looks something like this. It'll have d box, and then you'll have to type something in here, and then it'll have a line and then another box. So because on your calculator they use x for the independent variable instead of t, wherever there's a t in this equation, I will plug in with an x when I type the equation in here. And then down here is where I will type in the 23. Now, usually what I do on my calculator is I type the equation into y1 so that I don't mess up on it later. So this is what I would have entered into y1 on my calculator using x's instead of t's. And then here I type in y1 into this n-derive feature. And you can get that actually by hitting alpha trace on your calculator and it brings up the y1. And then let me do that now to see what value I get for my derivative. Oh, also make sure you're in radian mode. Okay, so when I plug that in my calculator, I end up getting a negative decimal. It ends up equaling negative 0.40769 yada yada yada, or approximately negative 0.408 would be my acceleration. So it also wanted us to indicate units of measure. So what we just did was the derivative of velocity. So this would be velocity units, which is miles per minute, divided by time units, which is minutes again. So it ends up being miles per minute, or miles per minute squared. So when they say indicate units of measure, that means they usually are giving a point just for that. So hopefully that's the case here. So lastly, with part D, this part is asking us to use that same model, this one here, the 6 plus cosine t over 10 model in part C, to determine the average velocity in miles per minute over the interval 0 to 40. So this is also just kind of checking to see if you know what or how to find average velocity. So that's when you just use the average value of a function formula. So average velocity would be 1 over b minus a integral a to b of velocity. So it's just the average value of a function formula applied to velocity as our function. And in this case, the interval is 0 to 40. So that means my integral here would be 1 over 40 minus 0 times integral from 0 to 40. And in this case, it's called f of t, not v of t. F of t dt, based on the name they gave it in part C, or 1 over 40 integral 0 to 40 of f of t dt. So I'm going to use the FNINT feature in my calculator to evaluate the integral. And when I do that, it basically looks just like this. It has a box here, a box there, a box in the middle, and then a box for the variable you're taking the integral with respect to. So I would plug in 0 for my lower limit, 40 for my upper limit, x for my integral that I'm integrating with respect to. And then I'm going to use y1 again because that's the same model from part C that I had already input in my calculator as y1. It just helps me avoid making errors from typing in long, complicated equations, and see what I get when I do that. So for the integral part, so I have the 1 over 40 part. For the integral part, I got 236.6507935. And then when I divide that by 40 to get the average, so this is my total miles traveled during the integral from 0 to 40. And then if I want to find average velocity, then it would be total distance traveled divided by total time that has passed. So when we divide by 40, and I get 5.916 if I round to the third decimal place, which is what AP test always requires. So it's 5.916 miles. That's the 236 part per minute. That's the 40 minutes part. So those are the units for part D. Okay, so we've got all our answers. Let's go now and check the scoring guidelines and see how we did. Okay, so here in part A, we can see that they allocated 3 points to that part. 1 just for choosing the correct y value to use for your midpoints, the 9.27, 2.4, and 4.3. 1 for the answer, which would be the 229, and 1 for the meaning. So yeah, total distance in miles during the first 40 minutes. So that matches our answer. In part B, they again reference the mean value theorem. So that's for that you need to do that for the justification, which is worth 1 point. And it looks like they gave 1 point just for mentioning the 2 instances. So, and their explanation seems a little less thorough, which is okay. But I still say to err on the side of being super overly thorough to make sure that you get your point across. But basically, they just mentioned derivative of velocity, aka acceleration, does have to be somewhere 0, somewhere in these 2 intervals by the mean value theorem. So therefore, at least 2 values of t will create a 0 value for acceleration. And then here you can see, yeah, they're just looking to see that you know that the acceleration would be the derivative of velocity, and you just have to find f prime of 23, which can be done on a calculator, and then there's the units. So it looks like just 1 point was allocated to that, and you had to have the units. So instead of giving a separate units point, it was like a condition to get the point. So if we hadn't put the miles per minute squared, then I don't know that we would have gotten the point for negative 0.407, or maybe they would have given half point. Not sure. But anyway, that was 1 point total. Then for the average velocity, they actually gave 3 points for that. 1 for recognizing the limits are from 0 to 40. 1 for recognizing we're just taking the integral of velocity. I think sometimes students think that when you're doing an integral to find velocity, it has to be the integral of acceleration, but that's not true when we're trying to find an average velocity. We want to find change in position over change in time. So we just want to integrate velocity, not acceleration, integrate velocity, and then divide that by the change in time, and that will give me the average velocity. So they gave 1 whole point just for recognizing that we're integrating velocity, and then 1 point for the answer, which is the 5.916. So that walks you through the first one. Your job now is to go through the rest of these. Feel free to email or text with any questions, and have fun. Bye.